Okay, so this is the TIFR registers, or timer counter interrupt flag registers. So here this register will contains the flag for different timers. So you can see the what we call that, the timer 0, timer 1, or timer 2 inside this flag. So here what we can have is that the so here TOV 0, OCF 0. So this is for timer 0. This is for timer 1, and this is the timer 2. So TOV for the overflow flag. So if the overflow flag is 1, for example, if this equals to 1, that means the method is the overflow method. Overflow method, or the second method. So if the TOV flag is 0, means that is the CTC method. So for the for timer 0 and timer 2, it's only have 2 bit. However, for timer 1, timer 1, you can see there is 4, because timer 1 will have 16 bit. 16 bit, which has lower and high, which refer to the A and B. That's why it is different. Next, so this is the normal mode or overflow mode. So here how do we read this? So initially this is the graph, time and TCNT. Time versus TCNT 0 versus time. So once the value of TCNT increase to 1, 1 high, high, it will go back to 0. So 0, this is high, means that once it arrive at the highest value it can have, which is 0FF, it will roll over. It will be 0, 0. So the TOV flag is high, 1. So same, once the TCNT increase until 0FF, it will roll off to 0, 0. Here it will be 1. So it just same. Same over the time. So the steps, how do we steps the program to use the timer 0 using normal mode? So firstly, we load the TCNT 0 registers. So we load the initial count value, and then we load the value into TCCR 0 registers, and then we determine which mode. Which mode means that is it overflow, is it CTC method, and then it will use the prescale or not. And then we monitor the TOV. If it rise, it will be high. And then if we want to stop the timer, so what we can do is disconnect it with the clock source. How to disconnect it with clock source, we just put the TCCR0 value with 0. Okay, so here we already stop the timer, and then we clear the TOV0 for next ground, and then we repeat the process again. Okay, so how do we see the TCCR register here? You can refer back to the previous slide of the TCCR. Okay, here, or this one. TCCR. Okay. TCCR. Okay, so the TCCR, you refer back to the earlier slide. So next, we move forward for the example of program using timer 0 in normal mode. So what we can see here is refer back to the time delay there. Okay, you refer to the time delay. Firstly, we load the TC and T values. So here it load with the F2. Okay, and then it load the TCCR0 with 01. Okay, so this is the initial value that we decide. So here 01, so TCCR. So what does it mean by 01 here? Okay, we refer back to the TCCR. Okay, TCCR. Okay, so the TCCR, it declared at 01. So 01 is here. Okay, why I choose this? Because we always read the values to be at the end of the at the most right of the bit. Okay, so in the code it says it's only 01. Okay, here 01. So 01 means that the TCCR is no prescaler. Okay, and then here the code input R20 TIFR. So it will read what is the value here. Okay, and then okay, SBRS R20 TOV0. So this is the overflow flag. This is TIFR flag. So we see what inside there, and then it will if TOV is if the overflow is 1. Okay, if the TOV flag is 1, means that we are using the overflow method. If TOV flag is 0, means we are using the CTC method. Okay, and then our jump again, we'll do this if it satisfies the condition. Okay, and then it load TCCR output R20. Okay, so it load TCCR with 00. It want to stop the timer. Okay, so that is it. This is the step, and then once it is written in the code, is like this. Okay, this is using assembly code. Okay, alright, so for the example here, calculate the amount of time delay generated by the timer. Assume that the crystal is 8 MHz. Okay, so the solution is that we need to calculate the time delay. So how to calculate the time delay? We know that we have the crystal over here. So the crystal speed is 8 MHz. So what we can have from 8 MHz is the time. Okay, the time is 1/8 MHz, which is 0.125 microsecond. And then we know that the T will be equals to 0.125 microseconds. So every ticks, okay, every ticks of the timer 0 for this code will resulting in 0.125 microseconds delay. So the question asks, calculate the amount of time delay. So how many amount is how many amount of time delay generated by the timer? So we need to know how much count. Okay, how much count? For this case, we have okay. So here, from the code, we can see the value of TCNT is 0F2. So this is the value that is provided in the code. So how we make use of the value is, okay, we know that the number of count, okay, the number of count for the rollover is 0FF, okay, the maximum. So the FF we minus the TCC and TCNT value. Okay, we minus the count value, therefore we get the 13. But then this 13, okay, this 13 is because we need to this value is not included. Okay, then we need to know that this 13, okay, this 13 value is from FF to F2. However, we still have that values from FF to 0, right? Because of this, if you refer back to the previous slide, we have this from FF to 0. Okay, so we need to add another 1 to complete our amount of time delay that is generated by the timer. So here we have 13, so we just add another 1, which is 14. And therefore our duration for the the time delay generated by the timer is 14 multiplied with the 0.125 microsecond. Therefore we have 1.75 microsecond for half of the pulse. Okay, so here we have we know the frequency, so we can measure the period 1 over F, and then the second we measure the delay. Okay, delay will be equals to T multiply, okay, T multiply with count, and also the third equation we can have the TCNT will be equals to FF minus count, okay, plus 1. Okay, so now we're using this equation. Okay, moving forward, steps to program timer 0 in normal mode. So here this is another example. Okay, so for the next example, in example 93, calculate the frequency. Okay, so it says calculate the frequency of the square wave generated on pin port V5. Assume that the crystal is 8 MHz. So we already calculate that the count. Okay, the count in the previous question is 14, right? Okay, so 14. Therefore, how do we estimate this? If we want to process this, what is the frequency? Okay, what is the frequency of the square wave generated on pin port B5. Okay, so this is the code which read at the pin port B5 here. So what we can do here from the code here, we get the cycles. Okay, we get the cycles. So these cycles you can find on the instruction set. Okay, so usually for the branch, okay, for the branch we will have more than one cycles lah. Okay, so here you just check on the instruction set and then you take note how many cycle it is. Okay, so here this is already given to you, so you just add that. Okay, so you just add the cycles number. So here it will 3113 ini semua you add. Okay, so this one, which one to choose? So here we choose one. Okay, because this is 0, right? Okay, so here from here 24. Okay, so all of these we will get 24 cycles. So how do we calculate the frequency? We need to find the f. Okay, so we know from the equation f equals to 1 over t. So how much is the t for this case? So here we already have the initial value is from the previous slide. We have the 14 and also we have the 0.125, right, microsecond, and also we have the count is 14. So here it wants to have the square wave, means that it wants to have the complete of the frequency. So for the values here that we get previously is only half of the frequency. So what we can do is, because it want to have the square wave, so we need to multiply it with 2. Okay, so we have the total number of count plus with the total cycles, and then we multiply with the time delay that we had initially. Okay, so it will give us a value of 9.5 microsecond. So we use this to calculate the frequency. So here for the question we have this 105 kilohertz. Okay, so the next step, how to find the values to be loaded in the timer. So if we assume, the amount of time delay is needed is known, if we know this, okay, we need to find the what we call that. So we need to find the we need to find the values that we need to put into the TCNT registers, and then the following steps can be used to calculate the values to load the values into the TCNT. So firstly, we identify how much is the T. Okay, how much is the T? 1 equal to F, and then we divide the desired time delay by the clock, and then we perform 256 minus n. Okay, 256 is in the decimal values, and then once the value we find the value, we convert the results into hex. Okay, we find the hex for the decimal. Okay, and that will be loaded into the timers registers. Okay, so that's it for this. And then how to, okay, so here lah. So firstly we find the time. How to find the time here as explained in this slide. So how do we transfer it into the assembly language? So firstly, we know that the time is 12.5 microsecond. So we also have the delay of 6.25 microsecond. Okay, and the crystal frequency is 8 megahertz, and we know that the count is every 0.125 microsecond. Every count that the length of 0.125 microsecond, it will count. So therefore we need to have 6.5 microsecond of the time delay here. We need to divide it with the count time. The count time is 0.125 microseconds. Therefore we have 50 clocks. 50 clocks mean we have 50 times 8 clocks it take. Okay, so here from this we know that we have the 256. Okay, 256, the FF. So the 256, the decimal value, we minus with 50, and then we got to 206. So we convert it to hexa. Okay, so this is the value of our TCNT, as simple as that. So we just put it into the code. Okay, that's it. And then for the prescaler and generating a large time delay. So what is defined by the prescaler? So no prescaler by 8. Okay, this one we have seen that in the beginning. Okay, the TCCR. So we have the prescaler 8. Okay, no prescaler, we have 8. No prescaler is here. 8, 64, 256, 0, 1024. Okay, so for example, we have the certain value of frequency. We want to scale it. Maybe the speed is too fast or too slow. So we want to reduce the speed, or we want to increase the speed. That's why we need to have this prescaler. Okay, so in which the largest time delay only achieved by making TCNT 0, 0. What if this is not enough? That's why we have the prescaler option in TCCR 0 to increase the delay by reducing the period. So the prescaler option allow us to divide the instruction clock, by factor of 8 to 1024. So that is why we see the prescaler 8, prescaler 64, 256 and 1024. Okay, so if the prescaler bit is enabled, we can divide the clock before it is fed into timer 0. Okay, so the lower 3 bits of TCCR 0 give the options of the number we can divide by 8, 64, 256 and 1024. So for example, here we have the following frequencies. Okay, 8 megahertz, 16 megahertz, and then we have 10 megahertz. So for example, we want to use the prescaler of 1 to the ratio of 64. Okay, so we know that if we divide 1 over 64, and then we need to multiply it with 8 megahertz, because this is the, for question A, okay, this is the original frequency that we want actually, but then we want to use the prescaler. So we have a prescaler, we want to use the prescaler 1 to 64, means that we just need to identify what is the ratio. Okay, what is the ratio, and we need to multiply it with the original crystal frequencies that is supposed to be available. Okay, available. So for example, actually it is 8 megahertz, and then you want to use the prescale of 1 to 64. Okay, so you find the value of 1 over 64 multiply with the crystal frequency 8 megahertz. Okay, so therefore you will have 1 to 5 kilohertz only. Okay, instead of you have 8 megahertz, you have reduce. Okay, you have rescale. Okay, you have rescaled the from 8 megahertz to 1 to 5 kilohertz. Okay, and therefore, because of the prescaler, your the T for each of the clock is only 8 microsecond. Okay, so before that you have the you have 1/8 megahertz, right? 1/8 megahertz, you have 0.125, right? Okay, 0.125 microsecond. So now instead of your clock takes every 0.125 microsecond, you increase the time to 8 microseconds, so it is slower. Okay, instead it's faster, we want to make it slower, so you get 8 microsecond. So same as if you have 16 megahertz, so if you prescale it using 164, you will get 4 microsecond. Okay, so dia lebih slow lah, it is much slower. Okay, so here we have the prescaler of 64 if we are using the TCCR 0. So how to know the value inside our TCCR registers is we refer back to the question. Okay, the question say is in normal mode, timer 0, prescaler of 64. Okay, so we refer back to the previous slide of the TCCR here, TCCR. So normal mode here, bit 3 and 6 is 00, and then the prescale 64, right? So you have this inside your bit 012. Okay, 012 is 011. Okay, so you need to make sure that you find the correct values for your TCCR according to the question. Okay, okay, so here you get 011. Okay, for prescaler 64, and then it says it is normal. Normal means bit number 3 here, 3 and 6, 3 4 5 6. Okay, 3 4 5 6 is 0 0 0, and then the others you just put it 0 0 0 because that one supposedly in more advanced topic which is not covered in our class. Okay, so we just focus on FOC 0, COM 010, COM 00, also 0. So this is for the serial communication. Okay, so this is another example. So you can find, you can read through. Okay, so here if we, okay, so this is the first method or CTC method, compare match. So this is not the overflow match, means that the TOV here, the TOV is 1, so the process will make use of the TCNT register and also SEER registers, compare. Okay, need to read the OCF value. If same, OCF will be 1. Okay, so here let's see. If same, OCF will be 1. So here is the graph. Okay, TCNT versus time. So once the values inside the register increase up to certain values, okay, TCNT equals to OCR. Okay, so if TCNT and so if this is the OCR value, we know that the TCNT will have the maximum limit of 0 FF. Okay, so if the TCNT value is it won't be greater than FF because this is not the overflow method. Okay, since our TOV is 0, this is not overflow method. So if overflow, if TOV is 1, that's where you can see the TCNT reach to FF values. Okay, but now we are using the CTC method or CTC mode, which to compare the TCNT registers and also OCR registers. So the value of TCNT will not, okay, will not exceed 0 FF. Okay, so if we have the timer there, Okay, timer 0. So once the value increase until OCR value, okay, so if the value same for both TCNT and OCR, the OCF will be 1. So it will return to 1. Okay, so the value increase back, and then until OCR value same with TCNT, it will be OCF 1. Okay. Why OCF 1? Because the OCF flag is set. Okay, once the values in TCNT and OCR are same, the OCF will be set. Okay, the OCF will be set and the timer will be clear. Okay, so it will count back. Okay, so the OCF flag is located in the TIFR registers. So this is OCF0. Okay, so we go back to the TIFR. You can see the here you can see the OCF values over there, and also the TOV. So if TOV is 0, the OCF will be either 1 or 0, depend on the comparator values of the TCNT and OCR. Okay, so this is the same. This is the step. So how much is the OCR value? It is 9, so it will be compared with the TCNT. If the value is same, it will stop the timer and it will clear the OCF flag. So this is same, actually the same explanation, only that here is the code and this is the command or the details. Okay, and next is clear timer 0 on CTC mode. Okay, so same lah, this is also we need to know that here we are using the prescaler 1024. Okay, means that due to prescaler 1024, each timer clock lasts 1024 multiply with 1/8 megahertz. Okay, 1/8 megahertz is 0.125 microsecond, which is 1 to 8 microsecond. Okay, so in order to get the time delay of the given here, we should wait for 200 clocks. Okay, so the OCR register should be loaded with 200 minus 1 because of the reset one, the clear time. So you need to minus 1. Okay, so you need to load the value of 199 into the registers. Okay, so here use register R20, so OCR 0 will be contain the value of R20, which is 199. Okay, so if it is same, it will skip, and then it will stop the timer, and then it will clear the OCF flag. Okay, so next is timer 2 programming.